So last class we worked on solving exponential equations and logarithmic equations. So we're going to use those skills and apply them to these contextual problems of growth and decay. Now, these words are not new to you. You've probably heard of growth and decay since Algebra 1 and Algebra 2 and Pre-Cal if you've taken that class. But as a review, exponential growth and decay is this formula here, A naught times e to the kt. Now, there are two numbers that we need to fill in to have the equation written. Because the e is a number, that's our base, t is our variable, but we need the two numbers for a sub 0, which is the initial amount, and then k, which is some growth factor. So let's highlight that for ourselves. A sub 0 is the original amount or size when we started, the initial value. And then k is just some value for the situation representing the growth rate. So k is the rate. If that k value is bigger than 0, then the function model shows growth. And if that k value is less than 0, some sort of negative number, that's when we're going to have a negative or a decreasing exponential decay function. So you have your two examples of what these graphs look like, which should be familiar to us. Almost all of these, I'm like 99.9% sure, they're all going to be above the x-axis because in real life, all of these values have actual value instead of a negative value. So we really only have these two options for what the graph is going to look like, an increasing and decreasing scenario. Most of them are going to start at time equal to 0, which is why this does not have an arrow going to the left. It has a starting place. Again, because this is modeling stuff in real life, usually as a function of time, and we don't time travel yet. So we don't go into the negative x values because we don't time travel. Let's just hop right in and see when or how we would use this exponential growth or decay formula. In example 1, it says the graph in the figure on the right shows the U.S. population in millions for 6 selected years from 1970 to 2020. In 1970, the U.S. population was 203.3 million people. By 2020, it had grown to 331 million. Part A wants us to find an exponential growth function that models the data for 1970 through 1920, and then use that information to predict the year in which the U.S. population will reach 4 million. Okay, here we go. When we're doing this, we want to fill in the formula from the top of our page, which is A equal to A sub 0 times e to the kt. We need an initial value or an initial amount. So since our study starts in 1970, we can use 1970 as our initial amount. How many people were in the U.S. in 1970? That would be 203.3 million people. We also need a k value. In the blurb right there, did it tell us the rate at which we are growing? So what we're going to do to find k is use the other input-output value that it gave us, which was in year 2020. It had grown to 331 million, as another input and output pair. Meaning I'm going to put the coordinate point 50, 331 into this formula somewhere. Now, where did I get the 50 from? The time. How many years after 1970 is 2020? 50 years. So 50 years after we started looking at this model, we had 331 million people there. So we want to fill that in the equation here so that we can solve for t. So time is 50. And the amount at that point is 331. So we are using another input-output pair to now be able to solve for k. Because if you notice, the only variable left at this point is k. So we can solve for it. But we need to remember our skills from last class and how to solve this type of equation. The first thing we did last class to solve was to isolate the thing with the power. So what do I have to divide by on both sides to get the thing with the power by itself? What's in front of this base that I want to go away? K is in the exponent. It's going to be this number right here, the a sub 0. So I'm actually going to divide both sides by 203.3, but I'm not going to put that in my calculator just yet because it's some sort of decimal and I don't want to round too early. But if I divide both sides by that, I have 331 divided by 203.3 equal to e to the 50k. Last class, what did we do after we isolated the base? We did something to both sides. We took the natural log of both sides. So we have the natural log of both the right side and the left side. Your spidey senses should be going off on the right side. What's going to happen that's really nice and simple on the right side? Yeah, the natural log and the e are going to cancel each other out essentially. So you're only left with that 50k. So I have natural log of 331 over 203.3 equal to 50 times k. Ooh, I'm one step away from solving for k. What do I have to do to get k by itself? Divide by 50. So in our calculators, which I know some of us are going to have to stand up and go get because I didn't remind you at the beginning of class to do that since you were moving my desks back for me. Thank you. We're going to divide all of that by 50 and we're going to get some value for k. And we're going to round it to the nearest 5 decimals today for this problem because it's kind of small. I'll pause. I'll let you go grab a calculator and evaluate for k. Okay, when you evaluate that, I know it's got a lot of fractions happening, we would get approximately 0.00975. A key point to all of this is you really have to pay attention to what the problem on the textbook is asking for you to round to because it will significantly affect your answers. So if it was solving for k, maybe it said round to the nearest tens, hundreds, that's a really small decimal, 5 decimal places, or it may, my gosh, words are hard today. It may say to round to the nearest hundredth, which would be approximately 0.01. That's the value of k we're going to use in this problem when we're plugging it in, but just so we know how we got that, there's the more expanded decimal. Wow, it's like I haven't spoken before. Hello. Okay, so, wow, we've lost the plot here. Why were we even doing this? Great question. So we had to do all of this business to find a value for k so that we could write that very original function. So if I'm answering letter A, which asked me to write the exponential growth function for this problem, how we would write that is we would say A is going to be equal to that initial value of 203.3 multiplied by e raised to the power we just found, which is 0.01 times t. We only really need to plug in the initial value and k. The only problem with this particular problem is that we didn't have k to begin with, so we had to solve for k first. Part B here asks, in what year will the U.S. population reach 400 million? Now, did they give us for 400 million, is that an input or an output? Output. So unfortunately, what we have to do with that 400 million is put it on the outside where the final amount would be. So the formula that the equation that I'm solving here is 400 equal to 2.03.3 e to the 0.1 t, or 0.01 t. But our steps are very similar to what we just did to solve for k. So let's repeat those steps. What should I do first to start solving for t? What did we do first here? Divide by 203.3. So I have 400 divided by 203.3 equal to e to the 0.01 t. What do I do on both sides? natural log. I'm going to take a shortcut here because I know that the natural log and the e are going to cancel. So on the right-hand side, I'm just going to write 0.01t because I know they cancel. I'm just trying to save me some space. What's the last step to solve for t? I'm dividing by that number in front of t. I just wrote the wrong number down, 203.3 divided by 0.01. Since we got k, I trust we can put this in a calculator, but at this point, without rounding early, we would round or would calculate here and evaluate that this is 67.678. Now, the question was, and this is going to be another point with these real world questions, make sure you're actually answering the question. It doesn't say how many years after. It says by which year will the U.S. population reach 40 million. So time being 67 means that it's 67 years after 1970. So our year is going to be 1970 plus this 67 years that we know have passed. So it is the year 2038. That's the year that we think the U.S. population will reach 400 million people. So what we've done in this problem is we've applied the solving skills from last time, taking logs of both sides, isolating the base and the power, waiting to calculate to the very end, all of those things, and we've applied it to a problem. Population growth is one of the main examples people like to pull out when we're talking about this sort of thing. Okay, I guess the bells are off because it is 1:07. That's when we said lunch was going to be today, right? Let's go eat. So our next example involves exponential decay and its use in determining the age of fossils and artifacts. This method is based on considering the percentage of carbon-14 remaining in the fossil or artifact. Carbon-14 decays exponentially with a half-life of approximately 5,715 years. And this is like legitimately how people carbon date stuff. The half-life of a substance is the time required for half of a given sample to disintegrate. Thus, after 5,715 years, a given amount of carbon-14 will have decayed to half of the original amount. Carbon dating is useful for artifacts or fossils up to 80,000 years old. Other objects do not have enough carbon-14 left to determine age accurately, but this is how we determine like straight up how old some stuff is, which is pretty cool. And you will have a lot of carbon dating examples to make sure we've nailed down. I'm going to tell you that right now. So it says, example 2, carbon-14 dating, the Dead Sea Scrolls. Use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount to find the exponential decay model for carbon-14. That is a fancy way of asking you to use that information to find K, because that's the one thing we will not have been given in this problem. So if we start with what we started with last time, knowing that the amount left over is equal to the initial amount times e to the kt, all we need to do, like we did last time, is figure out this k value and figure out the initial amount. Now this problem feels like it didn't give us enough information, but it actually did. It's telling us that we have made it to half the original amount in this many years. So it has given us a t and an estimate of the final amount. So if I was using the same colors as I did on the other side of this, this would be t, and this would be how we would figure out the output at that time. So what this is saying, again, just to give us a little bit more information on our notes, our time is 5,715 years. The other thing we had in the other problem was the final amount. That's what we got from the other coordinate point when we were solving for k. Well, the other coordinate point here says that the amount left over is half of the original amount. So I'm doing half of a sub 0, whatever was there to begin with, the original amount. So if I plug all of that in, I would have 1/2 a sub 0 equal to that a sub 0 times e to the kt power, or sorry, k times 5715, because we know the time. Now I still have two variables left in this problem because I didn't actually plug a number in for my initial amount, but we don't need it. I don't need to know how many there were. I just need to know that this is the half-life for this object. So what we're going to do on both sides is we're still going to divide by the orange thing. That's what we've done on the other paper. But when I divide both sides by a sub 0, won't this a sub 0 and this a sub 0 cancel each other out? Because you'd have a sub 0 on top and a sub 0 on bottom. Which means we have 1/2 equal to e to the 5715k as the only thing left in this problem. The a sub 0s cancel each other out. They've divided away. We use our skills to solve for k. So after we divide, we have the base with the power isolated. We take the natural log of both sides. So we're doing the natural log of 1/2 equal to the natural log of e to the 5715 times k. But we know the natural log and the e are going to cancel. So I have the natural log of 1/2 equal to 5715 times k. And I can do one final step like I've done in all of these processes and divide by 5715 to get the value for k. K would be equal to the natural log of 1/2 divided by 5715. No problem. And if you throw that into a calculator, you will get approximately, and we're going to use a lot of decimals here, negative 0.000121 as your k value. Now again, the fact that this is negative makes sense because if your k value is positive, your amount should be growing. And if your k value is negative, your amount should be decaying. And since we're looking at how much carbon is left because it's getting less and less and less when we're carbon dating these fossils, we should have a negative k value. By the way, I think if you plug this in your calculator is actually going to spit out to you negative 1.21 times e to the negative 4 power. That is, what's that called? The scientific notation, and it's telling you to move the decimal point 4 places to the left. So if you get a very small number in your calculator, it's usually going to show up in scientific notation. Yowza. Okay, so part A, remember, was wanting us to write a formula here where we had the k value. So A equal to a sub 0 times e to the negative 0.000121 times t. That's our formula, just basically plugging in the k value that we found. Part B here says, in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab Bowdin, I probably pronounced that wrong, herdsman. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. Estimate the age of the Dead Sea Scrolls. Okay, so if we kind of split our brain here, we just spent some time finding the value of this formula, and now we want to use the formula to actually carbon date some stuff. So it says that we have a final amount that is 76% of the original amount in the account, or amount in the object, which means that we are actually plugging in 0.76 times the initial amount of carbon-14 in this object. That's the only thing we need to solve for t. I'm going to zoom in. So if we're solving for t here, we would have 0.76 a sub 0, that's our amount, equal to a sub 0 times e to the negative 0.000121 times t. Okay, I still have my initial amount plugged in because it's being referenced on both sides of the equal sign, and then I'm using that k value we found in part A. The only variable I have left here is t, so we're solving for t. Steps are very similar. You're dividing by the initial amount, but again, because we have a sub 0 on both sides, they will cancel out because a sub 0 divided by a sub 0 is 1. So I have 0.76 equal to e to the negative 0.000121 times t. We take the natural log of both sides, and because I think we'll start to see this pattern, the natural log and the e are going to cancel each other out. So we can go ahead and do that step in one fell swoop. To solve for t, all I have to do is divide by that k value on both sides. So I will do natural log of 0.76 divided by negative 0.000121. We'll pop that into a calculator. And we get that the time for the Dead Sea Scrolls, or how old it is 2268.073. So these Dead Sea Scrolls are 2268.073, which means in 1947, when they were carbon dated, they were 2,268 years old. It's a very old piece of paper. But today, it is 2024. So how old are these things today? How many years past 1947 is it right now? That's a legit question. How many years have passed since 1947 to 2024? 77. So if we add 77 years to 2268 plus 77 years, if we were looking at these documents today, they are 2,345 years old, which is pretty cool that we know how old things are just by looking at the amount of carbon left in them. This is how we carbon date fossils. This is how we carbon date old transcripts and manuscripts and all the things we find in caves around the world, which is pretty cool. But notice the steps that we used to solve this were the same. We filled in what we knew using an input-output value. We divided. We took the natural log of both sides. We canceled the thing out. We divided. Over here, we plug all the things we know in. We divide. We take the logs of both sides. It cancels out. We divide. We have our time. The steps are going to sound very repetitive when you're solving these sorts of things because they're the same process over and over again. Pretty cool. Another thing that's pretty cool is a function type that we don't really discuss all that much in high school, but it's actually a very useful model for functions. It's called a logistic growth model. Notice that this does not say logarithmic. It says logistic. This is a different type of function, but it behaves with similar qualities of an exponential and a logarithm kind of at the same time, which is pretty cool. The mathematical model for a logistic function is this formula right here, and it looks terrifying. I need us to be able to use the formula and understand one or two important things about the formula, and that's it. Okay? As time increases, the expression a times e to the negative b to the t power approaches 0, and a gets closer and closer to c. This means that this line up here, y equal to c, is a horizontal asymptote of the graph. Let's highlight that in a color. We'll do this in green. We have this, what's called a limiting size of the function. So our function will grow very quickly like an exponential, but then we're going to have this maximum capacity for whatever we're discussing, right? Whatever the limiting size is that's going to like flatten the top of the graph back out again. So it starts initially like an exponential function, an increasing rate of growth. And then we have this point of inflection where we start to decrease our rate of growth. So we taper off at what's called, again, the limiting size. And it's whatever the number is in the top of the function. That's the limiting size of the function. One of the things that a logistic model models is the spread of disease. So typically we say the spread of disease happens exponentially, and it totally does up to a point. and then you will reach a maximum capacity for the spread of disease. Thus, it becomes a logistic function. So example 3 says the figure below shows the number of new coronavirus cases in the United States for 7 selected days in 2020. The function f of t equal to 26,462 over 1 plus 62 times e to the negative 0.53t models the number of new coronavirus cases in the United States t days after March 14th, 2020. We're going to use the model to determine the number of new coronavirus cases on March 14th, 2020. Does this overestimate or underestimate the actual number, and by how much? Okay, so if we're wanting to know what's happening on this specific date, how many days after March 14th, 2020 is March 14th, 2020? Yeah, it feels weird to say that sentence. How many days after it is that date? None. So the time that it wants us to plug in is 0. So we're looking at 0 days after March 14th because we're looking at March 14th. We're going to use this number and plug it into our formula and be able to evaluate. So I'm just asking you to do f of 0. Notice that the only variable in this entire crazy scenario is the t value. So all I have to do is plug into a calculator all of this mess raised to the 0 power, and we're going to get the number of people who were infected on the first day that we are studying the study on March 14th, the number of coronavirus cases. Yes. So just because this is a new function type, let's make sure we can actually type it in accurately. I almost said that word wrong. Accurately to our calculators. Plug that in, what do you get? I agree. So if we look, compared to the actual data, when the CDC, I'm assuming this is where we got this data, counted the number of coronavirus cases in the United States on March 14th, we can see in the table that on March 14th, how many coronavirus cases were there actually in the United States? So did we overestimate or underestimate it with our model? We overestimated by how many? By 6 cases, which is really not too bad, considering we're looking at the entire population of the United States. We overestimated by 6 people. Part B says, use the model to determine the number of new coronavirus cases on March 24th, 2020. Does this over or underestimate the actual number, and by how much? Okay, this time, the date we care about is March 24th, 2020. What does that mean for my t value? 10 days, because it's 10 days after March 14th. So this time we're just doing f of 10. And again, because this is a new function type, we want to make sure we can type it in correctly. Let's go ahead and figure out how many coronavirus cases we have on day 10 based on our model by plugging in a 10. Since you've already typed it in, just press up on your calculator, highlight it, press enter. It'll retype it all for you, and you can go plug a 10 instead of a 0 in. What did we get when we plugged that in? Very good. 20,208.0397. So if we look at the table again, this time we're looking at March 14th. Compared to March 14th, did we over or under, sorry, not 14th, 24th. Did we over or underestimate the number with our model? This time we underestimated by how many? 133 cases, yeah. Still not too bad, considering, again, we're looking at the entire population of the United States. Now, part C is going to be something new for us. It's the new vocabulary. It says, according to the model, what is the limiting size of f of t, of the new number of new coronavirus cases in the United States? Limiting size is going to be the location of your horizontal asymptote for this graph. But it's really pretty simple to find because all we have to do is look at the top, the numerator of the function. What is the limiting size here? What's that numerator? That is the limiting size of this model. Basically, this model is saying that no more than 26,462 people would get the coronavirus based on our model. We know from experience that might have been a little different, but based on our model, whatever that numerator is, that is the limiting size. Maybe you write that note for yourself, so it's the numerator. Whatever number is there is your limiting size. That's going to be the location of the top horizontal asymptote for this function. So logistic functions are the type of function you would see in real life. They are used to model real life things like the growth of viruses. When you have a maximum of the population, there will be a limiting size. So this is a function that you can't ignore. It will definitely be around when you're looking at graphs in the future.